computer, on the other hand, unfortunately doesn't know how to not crash. Sorry, I'm loading up PowerPoint because it just crashed on me. Be fine.
Okay. So, Adrian, did you start?
We are recording, and you should see it all on the top left.
Oh, yes. Very nice. Cool. Okay, so I think I'll just do the brief intro in case anyone else wants to join in the meantime. So today we're going to be talking about, this is the ZK Study Club, something we do every once in a while where we get together and talk about a paper or a video or some protocol. And in this case, we're going to talk about PLONK. And we are very, I can't say it any other way. And we're very lucky that today, actually, Zach, who is one of the co-authors, is going to actually share this with us and present. And we might have some other co-authors join, maybe. But yeah, I want to say, like, welcome to the study club, Zach. I know that I heard from sort of our chatter that a lot of people have been reading the paper today or in the last few days. I think we're pretty excited to hear more about it. So why don't you go ahead?
Of course. Well, thanks. I mean, thanks for inviting me. I'm looking forward to this. Yeah, I apologize in advance if this is just, this is the first time I've given this presentation, so it might, yeah, we'll see how it goes. How do I share my screen? Wait, I still don't know how to use Zoom. Here we go. Great. So if I do this.
Nice.
Hey, is it all working?
Yep.
Cool. Okay.
Can you guys all see that in big? Do you know how to?
Yep.
Yep,
nice.
Looks good.
Yes. Cool. So yeah, PLONK. Permutations for Lagrange bases for echumerical non-interactive arguments of knowledge. Something of a tortured acronym. So yeah, PLONK is a universal ZK-SNARK that only requires one trusted setup to like initialize like the crypto system, and then you can convert arbitrary like programs, arbitrary NP relations into SNARK circuits without having to run additional trusted setups. So yeah, this is first pioneered by the Sonic protocol, and so PLONK is kind of an iteration and refinement of some of the techniques that they were using with the addition of some Lagrange-based shenanigans. So I just want to go to start with what I really wanted to do is explain a bit of the rationale behind the decisions that led us to PLONK, and so to writing about PLONK and talking utter PLONK. Basically, if you want to make a universal ZK-SNARK circuit, like proving system, you need a few fundamental ingredients. You need a way of taking some computer program and representing it via a sequence of like, basic arithmetic gates or logical gates. That can be efficiently compiled into a zero-knowledge proof. You need a way of succinctly representing a large number of instances of these arithmetic gates, because that's where SNARKs get their succinct. You're basically the verifier is verifying a very large number of very simple statements in parallel, kind of. So you also need some kind of commitment scheme where the prover can succinctly commit to this kind of representation of an arithmetic circuit. And then the verifier needs to be able to very efficiently validate whether these commitments actually describe the proof relation that the circuit just describes. So how do we get there? So I guess just to start with, like most SNARKs, our fundamental arithmetic unit is this kind of is an addition and a multiplication gate, where our gates are explicitly fan in two. So you have two input wires. Technically arbitrary numbers of output wires, and the additions and multiplications are all done in the finite field associated in some finite field where the precise modulus is going to be defined by the specific polynomial commitment scheme we're using. You then want to create some kind of representation of an arithmetic circuit using relationships between relatively high degree polynomials. The reason for this is because evaluating polynomials, particularly in the context of elliptic curve cryptography, is very efficient. We have commitment schemes where basically somebody can commit to an encryption of a polynomial, and then a verifier can check this encryption is correct in almost constant time. So the number of, the amount of computation the verifier has to do scale with the degree of these polynomials, which means you could pack more information into them without increasing the verified complexity. And then that also gives you a very efficient way of evaluating your SNARK circuit, because if you take some polynomial, a collection of polynomials, you evaluate them at a random point. If there's some kind of arithmetic relationship between the polynomials that's supposed to hold, then if it also holds, if that relationship holds for like the evaluations of that polynomial, then with overwhelming probability, it's also going to hold for the polynomial itself. But naturally, larger numbers of terms and conditions apply to that. So anyway, that's kind of the overview of kind of the ingredients that we needed for PLONK. And so the way we achieve this is with this Lagrange basis. We're basically effectively encode vectors of variables as polynomials. The idea being, if you have some kind of if you have a vector of n elements and you want to encode them as a polynomial, you can basically literally just pick predefined x values your x-axis, and then just assign the y value of your polynomial to be the value of your vector element for like individual x-axis points. So you can see here this graph is basically these Lagrange polynomials for the range of integers between 0 and 9, where you can see that each one of these polynomials in sequence is going to be equal to 1 at one specific x value and then 0 at the rest. This is the kind of you can use this to encode vectors, because basically this is what you do is you take one of these Lagrange polynomials, and the ith vector element of your vector is going to become the coefficient that you multiplies the ith Lagrange polynomial. There are a few, obviously, complications as well, because we're working in a finite field, and it's particularly efficient to use, instead of just picking random arbitrary x coordinates, to use some kind of multiplicative subgroup whose order equals the size of your vector. Specifically, what we like, this always basically boils down to groups of unity, because they're particularly efficient to work with, and you can use a lot of fast Fourier transform techniques to compute and manipulate these polynomials. Well, basically, this Lagrange polynomial that I have on the slide, what this is saying is basically if for Li of x, if x is the ith root of unity in this subgroup, then it's going to evaluate to 1, and if it's any other root of unity, it'll evaluate to 0. And then you can create linear sums of these Lagrange polynomials to define a polynomial that encodes a vector. And so how this can then be used to evaluate arithmetic circuits is because you can effectively take any arithmetic relationship which holds between your vector elements, and it will also hold when you perform those arithmetic operations on the polynomials that you use to encode your vectors, where effectively the vector arithmetic, if you have some kind of relationship between your vector elements which equals 0, then if you encode your vectors into Lagrange polynomials, then that arithmetic relationship will hold when you manipulate these polynomials, but instead of it equaling 0, you'll end up with a polynomial which is going to be 0 modulo the vanishing polynomial of your subgroup. So basically, so this ZH, this vanishing polynomial we have, it's going to be equal to 0 at every single member of the subgroup. And so what I've tried to show in this graph here is the red, blue, and green polynomials. They are like 3 polynomials that represent A, B, and C. So they've encoded some vectors such that if you take the dot product of those vectors and then add A and B and then add C, the result should be equal to 0. And so you can see here that result in polynomial form is going to be that orange function f4. And you'll notice that it passes through 0 at all of the x values between 0 and 9, because that's the, this isn't using roots of unity. This is just kind of a bit of a toy example. You see, that's the general principle.
Zach, can I just want to cut in for 1 second just to tell, because I don't know if you guys keep hearing that doorbell. It's basically anyone who's dropping off over and over again, maybe just stay off and we'll share a video of this. just because we're hearing that each time you join, just so you know. Keep going. Sorry, Zach.
So I can mute my machine, but then if anybody asks any questions, I won't be able to hear. So by the way, everyone, feel free to interject and ask questions. Like if there's something you don't understand, it's please ask about it. I suspect you won't be alone. So basically, yes, you take vectors, you encode them into via these Lagrange bases into polynomials, and then any arithmetical relationship which held on the vectors will also hold for the polynomials modulo this vanishing polynomial. And this is kind of the essence of what makes PLONK so efficient, because if we consider the degrees of all these polynomials we're working with, these A's, B's, C's, they are equal to the number of, the degrees equal to the number of elements in your vector, well, -1. And so you don't have any kind of overheads or bloating factors from this representation. So effectively, in a SNARK form, the degrees of these polynomials is going to be equal to the number of arithmetic gates that you have, and no larger, which is rather useful. So now that we have a way of encoding vectors as polynomials, we need a way of actually describing an arithmetic circuit. But now we can actually start talking about vectors instead of polynomials, because we have an abstraction layer which allows us to convert vectors to polynomials, which makes kind of circuit arithmetization a little bit easier to understand conceptually. The idea is we have these addition and multiplication gates that we need to construct a circuit out of. And so we can represent the wire values going into these gates as WL, WR, WO, and then we can also define vectors of these wire values. And similarly, if you want to kind of create addition and multiplication gates via like basic vector operations, so dot products, additions, you can do it with this concept of like selector vectors. So you can see here on the left-hand side, when we've described the multiplication gate, we have these gate constants Qm, Qo, Qc for multiplication, output, and constant. The idea is the multiplication selector will multiply the left and right wires by some constant factor. Similarly, you can also scale the output wire, and you can add in a constant. This allows you to like create relatively expressive, describe relatively expressive situations. If you need to scale some of the wires by a constant, you can do so. You want to send some of the wires to 0, you can do so. Similarly, you can do the same with addition gates, where instead we now have these gate constants, QL for the left wire, QR for the right wire, and then similarly we have QO and QC for the output wires and the constant. And you can define an addition gate in the same way. But the interesting thing here is, well, we don't really want two separate arithmetic expressions for our addition and multiplication gates, because when compiling them into a zero-knowledge proof, you then need to have separate equations to verify your addition constraints and your multiplication constraints, and then you need some way of mapping between the two. So like which wires from the multiplication route, like gate realm, connect into the addition gates, and that's difficult to do. Just for a bit of context, this is something that, for example, Groth 16 SNARKs don't have to deal with, because what Groth did was specifically construct the common reference string, like the trusted setup reference string, in such a manner that the only way you can construct satisfying proofs is if the relative linear relationships between all your y values have been satisfied. Effectively, addition gates are free in Groth 16, or close to free. But you can't really get that in universal SNARK, because you can't manipulate your setup process to suit the arithmetic needs of one specific circuit, like you can in Groth. So you need to deal with addition and multiplication, and find some way of like elegantly doing this without massively increasing the degrees of all of these polynomials you're committing to. So something that we noticed relatively early on was basically, well, we have these selector vectors and they can be 0. So why not just combine addition and multiplication gates into one arithmetic gate? Specifically, just take these two gates we had previously and just mash the equations together, and you have one relatively large equation between these vectors, which just can either describe an addition gate or a multiplication gate, depending on which of these gate constants you zero out. So obviously, to give an example, if a specific addition gate if a specific gate needs to be an addition gate, then Qm will be 0 for that specific gate. And if you want it to be a multiplication gate, then you'd send QL and QR to 0. So this gives us a really relatively compact representation of an arithmetic circuit in Lagrange-based form. You can take your vectors of y values and use Lagrange bases to turn them into polynomials. Similarly, you can do the same for your gate constants. And then you get some circuit-specific polynomials. So these Q polynomials are going to define one specific arithmetic circuit. And again, like that equation that we had over the vectors on the left-hand side, you can turn that into an equation between polynomials on the right-hand side pretty much directly, which is rather convenient. And you can notice also here that the degrees of the polynomials you're computing to don't blow up too much. So you can see that you have one time here where we're multiplying 3 polynomials together, which means that the right-hand side of this equation is going to be, so for n arithmetic gates, the right-hand side is going to be a degree 3n polynomial. And so I'm using here as a kind of shorthand saying, oh, this relationship is at 0 modulo the vanishing polynomial. Well, when it comes to actually checking that in a zero-knowledge proof, you need to prove that, which means you need to compute the quotient polynomial, basically the polynomial that you multiply the zero polynomial, the vanishing polynomial by, for this relationship to hold, and you prove that there is no remainder term. And so that quotient polynomial, its degree right now will be 2n because you're dividing by the vanishing polynomial, which is degree n. So basically, you can see the degrees of your polynomials aren't increasing very much, which is good because
is this different from, like, did the Sonics in Sonics, do they not do this?
So in Sonic, their arithmetization is somewhat different, where instead of using Lagrange bases, they encode like wire values for their multiplication gates as the coefficients of a Laurent polynomial. So basically, powers of x, effectively. And so like each unique power of x will be associated with some kind of y value. And so one of the upsides of that is it means that these polynomials are relatively nice to manipulate and work with because you're not having to do this rather odd Lagrange interpolation thing. But it does quite significantly increase the degree of your polynomials because you don't have a relatively compact way of testing a relationship between the polynomials. What you do in Sonic is effectively, if your arithmetic relationship holds, then you have a polynomial relationship where the constant term of that polynomial should be 0. But to get that, you then need you need to extend your polynomials into negative powers of x. So that to start with gives you a bit of a degree, blows up the degree by a factor of 2.
Okay. Does anyone else have any questions up to now? I'm just going to throw it out there.
I have a question.
Sure.
So basically the same thing that I asked you on Telegram, like these multiplicative subgroups, like how do you derive them?
So
because you need them to be like the exact size of your input vector, right? So if you make it too big subgroup, then you have a lot of extra computation to do, which you don't want to do.
Correct. That is true. So effectively, it is a slight. When you're assuming that this kind of proving system we've instantiated over a pairing friendly linear curve, you want the number of points on that curve, so the order of the curve group, to be a value that has a large number of these roots of unity. But obviously, you're not going to have a one-size-fits-all solution. So the standard technique, this is what the ZK team did, and it seems to be quite like a canonical way of deriving these curves, is you find a group order, a curve order, where a large number of powers of 2 are like nth roots of unity. So you can say like 2 to the I from I equals 0 to say like 28 or 30. You will have that, that will be a primitive root of unity. You'll be able to find the 2 to the nth root of unity in that. And so that then means that you effectively have to add dummy constraints into your circuit until the number of constraints you have equals one of those nice powers of 2. And so there is an inefficiency factor there. To give an example, I believe the ZK team worked extremely hard for their sampling release to ensure that their circuits were efficient enough that they could basically like the number of constraints was like just beneath a power of 2, and it gave them like a massive speed up. Did that help? Or
yeah, that pretty much answered it. Thanks.
Just awesome. So yeah, before any other questions?
I guess keep going.
Cool. Right. So I think we've kind of got to the end of the PLONK characterization. So it's probably worth taking stock of where we are right now, because we do not have a SNARK. What we have is a way of very, very efficiently validating that the kind of the inputs and outputs of a vector of a list of arithmetic gates are satisfied. So like basically, the inputs to your addition gates match the outputs, the inputs to your multiplication gates match the outputs. But what you don't have is, at the moment, any way of connecting these wires together, which is a little bit of a problem, because you don't have an arithmetic circuit without that. What I've tried to describe in these two diagrams is the bottom picture is kind of where we are right now, where every single gate is isolated. Its wires aren't connected to any other wires. You can't derive any meaningful information, any meaningful relationship between what do these gates. These things don't feed into anything. They're not connected. And what we really want is a situation like the picture on the right, where I've tried to kind of just visualize the fact that actually the relationships, the mappings between all the wires in an arithmetic circuit are not going to be nice and linear. You're not going to have like a layer of gates, where the outputs feed into the next layer of gates, and on and go. These wires are going to be routed all over the place and connecting to all sorts of different gates from all over the whole circuit. And you need a way of representing that. You need a way of verifying that this is if somebody's claiming to assert a satisfying proof for your circuit, you need a way of checking that they've actually connected up their wires correctly. This is the kind of sticking point for all universal SNARKs, because you can't, like in graph, you can't really add in structure into your reference string, which kind of forces these wire routing relationships to be satisfied. You have to check it somehow. So I just want to kind of to try and disambiguate what I'm talking about when I'm talking about connecting wires. If we have this example here, this very simple example of one gate feeding into where the output wire feeds into the left wire of a second gate, that's a connection. So you have two gates, gate 1 and gate 2, and there is an output wire for gate 1, and there is a left input wire for gate 2. It looks like they're the same in this diagram, but they really aren't. And you need a way of proving that the values on those wires are identical for this toy little circuit. So what we really need is a way of describing the circuit's copy relationships. Basically, which wire values, for a given program that's converted into arithmetic form, you're going to have a list of wire values that need to be the same as one another. And if they aren't, then you haven't got a correct set. You haven't got a correct proof that you've run the program correctly, because you've not connected your wires up. So to try and kind of capture this, I like to try and I like to think of basically consider all of the wires in your circuit and in one giant vector. So where here I've listed all the left wires and all the right wires and all the output wires, and these are all going to be unique wires, but they won't have unique wire values, if that makes any sense. We want to check whether various indices of this y vector contain copies of other indices. And specifically, what we really want to actually do is create two polynomials where the roots of these polynomials are identical if and only if the y copy relationship is satisfied. This is a little bit abstract, but this is something that we can actually test for in a zero-knowledge proof quite efficiently. And Lord knows we can't check, we're not working with vectors. The vectors are kind of an abstraction, so we can't really, we don't want to basically, the absolute last thing you want to do is iterate through your circuit constraint by constraint, and have validate that the wires have been connected correctly, because that you wouldn't have a SNARK and it wouldn't be succinct. The verifier would, its running time will be rather large, and that's what you have with this kind of helped sonic idea. So we can solve this with one of these dreaded permutation arguments, and I'm going to try and kind of capture the rationale behind it, where basically if you have your vector of wires, you can also create a vector which kind of just describes the y indices. So, from 1 to 3n, because you have n gates, so 3 n y's, you can map each y value to a unique index. Then you can also define a permutation function, where this function will map a wire index to a copy index. And by that I mean, if, say, for example, the first and the third and the fifth wires are supposed to be identical in your circuit, then you can say that the permutation function will map index 1 to 3, it'll map index 3 to 5, and it'll map index 5 to 1. The idea is, what you're trying to say is, the index at 1, the value at 1 should be equal to the value at 3, which should be equal to the value at 5, which should also be equal to the value at 1 again. And obviously, this one can only, if you can prove that, then you've got your correct copy relationship, and so your wires have been connected to the various gates correctly. And so, for further clarification, every copy cycle needs to be closed to define copy relationship. So basically, it's got to loop back in on itself. So the last copy permutation has got for a set of wires that are supposed to be the same, the copy permutations have to iterate through one another such that each sigma, the permutation function on each index will map to a different index. So to give an example here, you can see at the very end here, we have in our toy example, sigma 5 maps back to 1. So it kind of closes that loop. And obviously, if you have a wire index that isn't copied anywhere in the circuit, so it's genuinely unique, then the permutation function will just map to it. Why are we doing all this? Well, the idea is we can then create a vector that maps these indices, your vector indices, to the copy counterparts. So you can basically just list so basically what this vector is doing is basically saying, okay, apply this permutation function to each index in sequence, and then just list the result in this vector. The reason why this is useful is because this is one way that you can perform a permutation check. So what I have in this box here on the right is two field elements, where basically I'm just saying, take the wire index, combine it with one of these permutation vectors, multiply the permutation vector by some randomness, and then add some randomness, and then do that for every single constraint and multiply them all together. Why is this useful? It's useful because if z1 equals z2, you've got a satisfying permutation argument, and I'm going to try and explain why on earth that is now. And it basically relies on this thing called the Schwarz-Zippel lemma, that effectively, if you have some kind of polynomial identity that holds at a random evaluation point for your polynomials, then with overwhelming probability, it's going to hold for all your evaluation points. Basically, if you have two polynomials, you evaluate them at a random point, and the point evaluations are the same, then with overwhelming probability, these polynomials, they share the same coefficients and they share the same roots. Again, obviously, terms and conditions apply here. The degree of a polynomial needs to be significantly smaller than the characteristic of the prime field that you're kind of working in. But for us, that's the case. These polynomials, the degree is never going to go beyond a few million, or maybe 100 million. But the characteristic of the field is going to be like 2 to the 250 or something. Basically, if we look at the top right is where I have these z1 and z2 relationships. But you can use the Schwarz-Zippel lemma because basically those betas and gammas, they're random, right? So they're effectively, you can also say that you're effectively evaluating a polynomial at a random point, gamma. So here I've rewritten z1 and z2 as polynomials in x, where you then convert x into gamma. And if z1 equals z2, then these polynomials with overwhelming probability are going to be equal to one another as well. And so what you can tell from that is if this is the case, then the roots of these polynomials are going to be the same. Obviously, they're going to be like in different orders, kind of, if you list the roots. Like each product term in P1 of x is going to be equal to one of the product terms in P2 of x, but just in a different order. So what do you get from that? Well, okay, now let's zoom in and think about the case where you have two matching roots to these polynomials. So you know the roots are the same, so let's pick a root from P1 of x and a root from P2 of x equal each other. And you have this relationship wi plus I beta equals wj plus the permutation function on j times beta. So I and j are basically two indices of the vectors, the y vectors that we were using before. Beta, though, is also random. So again, we can then lean on the short simple number again. In the same way that we replaced gamma with saying, okay, gamma is a random variable, so you can then basically replace it with an indeterminate value and say this is now polynomial, and these polynomials hold. You can do the same with beta, which means that you have two degree 1 polynomials, wi plus ix equals wj plus the permutation function on j times x. And again, if these polynomials are equal to one another, so are their coefficients, which means that wi equals wj when the permutation function on j equals I. And so that permutation function was defining the copy relationships, right? So in our toy example, we were saying if y is 1, 3, and 5 are the same, then the permutation function will map 1 to 3, which means w1 will equal w3 if this permutation check holds. And similarly, it'll map 3 to 5, and so w3 has to equal w5 if this permutation check holds. And similarly, 5 maps to 1. And so you can repeat that for your entire circuit, basically. You define all of the copy relationships, and you create that permutation, you create a vector out of that permutation function, and then you use that in this kind of grand product argument. So compute these values z1 and z2. And if they are the same, then with overwhelming probability, your permutation is being satisfied, which means that you then know that the relevant, like all of the y values in the proof that's being presented to you, they satisfy the copy relationships of that specific arithmetic circuit. Does anybody have any questions? Because I have to admit, I've never successfully explained the permutation check to anybody ever.
Yeah.
Hello?
Yeah, I have a question. It's very elegant. So is Sonic also using some similar like permutation tricks?
Yes. So what I should have added at the very start was a massive attribution to Sonic, because Sonic pioneered the use of a permutation check to create a succinct SNARK. So a lot of these techniques were taken from the Sonic paper. Sonic used their permutation check in a slightly different way. So where we're basically using this permutation check to check copy relationships on the y values, what Sonic are doing is they're effectively using a permutation check to, well, the permutation check really, for them, it targets the, so if you go back to the earlier in my talk, pardon me, we have these Q polynomials, which defined these kind of constant coefficients for the gates. And Sonic uses the permutation check to basically ensure the prover has correctly constructed these constant coefficients correctly. So it applies it in a very different way, but the mechanism, the techniques are still the same.
Okay. And the degree of the polynomial here is 3 times n, right?
Yes.
And the polynomial, the degree of the polynomial used in Sonic, is it also like 3n or something?
So it's about 3. I must commit. I'm confess I'm on shaky ground talking about Sonic's permutation, like the degrees of all its polynomials. I think the Sonic permutation increases the degrees by 3, and you start with Laurent polynomials. So they're and then you also, something we were really focusing on PLONK was basically reducing the number of permutation checks, because these things are expensive. And so we only have 2 for the entire circuit. And that was one of the key kind of innovations that we were targeting, was to kind of reduce these number of permutation checks down to an absolute minimum.
Okay, very cool. Thank you.
Cool. I guess I'll carry on, because there is a massive elephant in the room that I haven't talked about, which is these product terms. How do you compute them when you're working with Lagrange bases? Because, okay, so we had this abstraction where I was talking about this vector of all y values, but we don't have that. We have polynomials which represent vectors for left wires, right wires, and output wires. But that's no bother. That's easy to fix, because basically we take that permutation vector we had from before, and we split that down into 3 components as well. So we have that identity permutation, which was just like literally just a list of integers increasing in value. You can split that down to 3 different polynomials, and similarly you can do the same with your copy permutation vector. And then you have at the bottom here, I've written out basically the how do you actually compute that product term? Because if you take these polynomials described at the bottom, the Lagrange coefficients of these polynomials are going to be the same as the coefficients as the product terms that you're multiplying together in Z1 and Z2. So great. That's useful, but now, okay, fine. So now you have, if you compute these polynomials, each Lagrange, you need to now compute the product of each Lagrange coefficient to get the grand product. Oh, so just a bit of disambiguation. By Lagrange coefficient, I mean like the thing you're multiplying the Lagrange polynomials by, because like, technically they aren't polynomial coefficients, so I'm just calling them Lagrange coefficients. To do a grand product argument, you basically, again, highly similar to Sonic. You effectively have a very simple SNARK circuit again to do a grand product argument. You basically have a long sequence of multiplication gates where the outputs are feeding into the inputs of the next multiplication gate. And so what I try to write out here is basically this is the right wires are going to be the Lagrange coefficients for those polynomial terms I mentioned before. So here we're computing the grand product for the identity permutation. So here's the problem, right? Breaking out these Lagrange coefficients and indexing them individually, we have this large product term at the bottom, where for the ith Lagrange polynomial, like the ith Lagrange coefficient, if you take the product of all these y's and permutation value coefficients, then if you multiply them by some z value in a vector of z values, then if that's equal to the next z value in the vector, then you have this. Then that describes this kind of this multiplication ladder thing, because you're saying basically there that the output, if z represents output wires, then the output wire, the output wire. Sorry, if z like I represents output wires and z if zi represents left wires, and zi plus 1 represents output wires, then you can say that basically like the circuit's left wires, if you take the vector of the circuit's left wires, that's exactly the same as the vector of the circuit's right output wires, but right shifted by 1. And here's the problem, right? Because I've been talking about vectors, but we're working with polynomials. And whilst you can conceptually, it's relatively easy to do a right shift on a vector, how in the blazes do you perform right shift on a polynomial's Lagrange-based coefficients? It's a bit of a difficult problem, and this was really one of the inciting incidents which led us to develop PLONK, was realizing that you can actually do this. Specifically, the fact that we're using multiplicative subgroups is one of the key reasons why you can perform this kind of weird right shift thing. Because if you consider like a multiplicative subgroup of order now n plus 1, because the size of these vectors is going to increase by 1, so you need to increase the order of your subgroup by 1. And we have a generator, omega, of the subgroup. And so this is going to be, like practically, when implemented, this is going to be the n plus 1th roots of unity in whatever prime field you're working with. And omega will be the primitive root of unity. So the ith Lagrange polynomial is going to be this weird product term where basically you're taking the product of x minus the primitive root to the power of j, they're dividing it by like the root u that's associated with this the L-ith Lagrange polynomial, the ith root, minus the omega to the j. What this is basically doing is in this product term, if x is any of the roots of unity that isn't omega to the I, then there's going to be one of the numerator terms will be 0, which means the Lagrange polynomial will be 0. And if x is w omega to the I, then the numerator will equal the denominator, so it's going to be equal to 1. Again, you just have this is a delta function, where if you evaluate Li at omega to the I, it's 1. If you evaluate Li at any of the other roots of unity, it'll be 0. So here's the thing. What happens if we take this Lagrange polynomial, but instead of evaluating at some indeterminate x, we evaluate it at indeterminate x divided by the primitive root? If you do this, then if you consider the product term, well, x is now divided by a primitive root. So you can factor that out. You can take in the numerator that omega to the j term, you just multiply it out by omega. and then you can factor out the term omega to the -1. But then if you do that, then you can then include that in the denominator by just increasing the degrees of all of your roots by 1. And so if you do that, well, consider what happens in this product term when j equals n plus 1. Then the numerator, you'll have the primitive roots, x minus primitive roots to the n plus 2. But this is a multiplicative subgroup. It's cyclic, right? So omega to the n plus 2 is equal to omega. So this thing cycles around, basically. What you have is that product term, you've effectively shifted all of your omegas up. You multiply them all by the primitive root. And so if you consider the term in this product that you're skipping, before you were skipping the ith root of unity, but now you're skipping the ith to the 1 root of unity, because you just multiplied up all your roots by the primitive root, which means that the ith Lagrange polynomial, when evaluated at x divided by the primitive root, is the same as the ith plus 1th Lagrange polynomial evaluated at x, which means that if you commit to some Lagrange-based polynomial, and you evaluate it at 2 points, you evaluate it at some z, and then also some z divided by the primitive root, then your second evaluation, like the Lagrange coefficients of that polynomial, will be the same as the first, but they've all been shifted by 1 to the right by 1, and so that gives you your right shift. That gets you. So if you go back a slide, so in that long product equation on the end of the left-hand side, where you have z, the ith index of z, and then you want to subtract the ith index, the I plus 1th index of z. Well, now you can just commit to one z polynomial and just evaluate it at 2 points, where the second point is just the first divided by the primitive root of unity, and that's how you get your. That's how you can get. that's how you can compute a grand product argument. And so this is the permutation argument stitched together into something which is attempting to be a coherent whole. So yes, I was told to not keep it too high level because it's quite a technical crowd. So yeah, here's some maths. Basically, what we have here at this kind of first rank of boxes, you have the identity permutation, like that vector encoded as a Lagrange polynomial, and again, because you're just listing vector elements, that's very simple. It's just I multiplied by the Lagrange polynomial. You then have the 3 permutation polynomials. You can actually skip out the other 2, the second and third identity polynomials, because they're basically just equal to n plus the first identity polynomial and 2n plus the second. The third identity polynomial is equal to the first plus 2n, and the second is equal to the first plus n. And so what you can do is you can now there's the z1 and z2 vectors we were talking about before. You can encode them also as polynomials, where effectively this is your grand product, where you're iterating over all of your constraints, and at each layer you're basically computing this grand product, where the number of terms in that product is going to be increasing by 1 up until you hit n. And you do that for z1 and z2 for the identity permutation and the copy permutation respectively, and then you have these 4 polynomial relationships, which, if they hold, mean you have a satisfying permutation argument. You can see here in the first relationship we have it's exactly the same as if I go back 2 slides. This product relationship for one single round of like coefficients. This is now that encoded. Encoded in polynomial form, where because these aren't vectors anymore, this thing isn't equal to 0, but it's equal to 0 modulo the vanishing polynomial. Again, with one extra caveat, which is now our vanishing polynomial, the order of our subgroup is now 1 greater than the number of constraints we have, because for the grand product argument to work, you need 1 extra element of the subgroup to cycle around. So our vanishing polynomial is now like the old vanishing polynomial, but you're just dividing out that last term that you don't care about. And so similarly, you have the same relationship for your copy permutation, and that should be equal to 0 modulo vanishing polynomial. And if those 2 equations are satisfied, then z1 and z2 represent grand product, the grand product arguments for your permutation checks. And then the only thing to do is you need to check 2 things. One, that the first coefficient of both of these grand products is the same, so they have the same starting point. So to go back to that circuit diagram, I said here that it starts out with left y being equal to 1. Technically, it doesn't have to be equal to 1. It's just that both grand product arguments need to start at the same point. So that's what you're checking with the third argument here. And then the fourth polynomial evaluation, you will now checking that the grand product terms for your identity permutation and the copy permutation are both equal to one another. So you're taking what would have been the nth first coefficient of your grand product polynomials, but you shift it down by one by evaluating it at x divided by omega. So you can then use the nth Lagrange polynomial to kind of select it out. This is also necessary because your vanishing polynomial now doesn't have that last nth form term in it, so you can't like select out the nth form term and make any kind of like argument about what that relationship should be, because your vanishing polynomial isn't correctly formed. Right. Okay. So this is the last slide. So sorry, I know this has been a bit of a that permutation argument. Well, I've done my best to explain it. Hopefully, it wasn't.
No, it's been super helpful. I think
you.
I'll have to like read the slides again. If you could send the slides, that would be great. But
I will do.
very
I will do.
helpful.
And so finally, if you want to put it all together, at least in polynomial form, you have 5 verification equations, right? There's 4 that we had for the permutation, and then that 1 equation for the arithmetisation. And I've been saying here everything is 0 modulo the vanishing polynomial, yada yada yada, but you actually need to prove this, which means you need to compute what that quotient polynomial is going to be. What do you multiply the vanishing polynomial by for this relationship to hold? And so that's this T of x polynomial, where effectively you can roll all these equations into one by just taking some random r and like multiplying each verification equation by some linearly independent bit of randomness. What this all means, putting it all together, is basically if you want to construct one of these proofs of knowledge for a circuit, you need to compute the coefficients of 6 polynomials, 3 for the y values, 2 for the grand products, and then this T of x quotient polynomial, where the degree of the quotient polynomial will be 3n, because like the numerator is degree 4n and the denominator is degree n. Additionally, if you're wanting to use Cat polynomial commitments, you need to, we're now evaluating these committed polynomials at 2 points. So you need 2 group elements for your opening proofs, which encode a degree n and a degree 3n polynomial respectively, because you're opening T of x on one of them. And so the overall cost for the prover, if you kind of ignore the fast Fourier transforms, which, I mean, obviously for really large circuits, that's not appropriate, but like generally, like the dominating cost of these things of constructing proofs is going to be the elliptic curve scalar multiplications. You need 12 of them for each constraint that you have, which means 12 times the number of arithmetic gates, which depending on your circuit structure can be extremely efficient. Obviously, comparing to something like a Groth circuit where addition gates are free, if you optimize your circuit under that assumption, then if you then turn it into PLONK, it's going to give you it's not going to give you a great result. But I mean, again, maybe some people in the chat can have more experience with this than I do, but I just basically running through some basic examples of the common algorithms that you tend to snarkify. I was getting basically like between 2 to 3 times the number of addition gates per multiplication gate, which means that generally this is pretty efficient. It's kind of like between 3 to 5 times slower than a Groth 16 proof, but compared to succinct sonic, it's the degrees of all your polynomials are quite a lot lower, so it should be quite a bit faster.
Do you think the compilation tools could be tweaked to not cost addition gates as 0? And how much would that change?
This is something I'm very intensely focused on at the moment, and quite a few people at the at Aztec, which is basically writing some of these compilation tools kind of from scratch, because we want to create, like, what we're trying to do is create quite a nice, like a clear abstraction layer between a SNARK program and the actual zero-knowledge proof it can pass down to, so that you can focus on writing like reasonably nice high-level SNARK languages without having to then also like wire them into a proving system. So basically, we're creating a kind of virtual machine environment with some very low-level opcodes to kind of assemble both the constraints of your SNARK, so those Q vectors, and also the actual Y values for a satisfying proof. And then the idea is then you can take a high-level language and compile it down theoretically to these low-level primitives. Anyway, so yeah, basically, I'm sure existing tools can be adapted, and I'm very excited about that. And we're also trying to do a few things from the ground up, because of the relatively unique arithmetic structure of PLONK.
Are there any other questions?
I think there was a typo in the last slide. Like
Yeah, probably.
In the chat, like the last term should be ln of x, right?
You're absolutely right. Yes, it should be, and also those z should be evaluated at x divided by omega. Yeah. Thanks for spelling that.
Okay, Zach, I have another question. Because I wanted to know if your techniques could improve the current, for example, confidential transaction implementation.
The current, I didn't quite catch that.
For confidential transactions, basically, there you don't. I guess we don't need like multiplication gates. We only need to have addition gates involved. So if we use the same tricks or same like techniques you used in PLONK, do you think that we could improve, for example, range proofs, this kind of stuff?
Interesting. So it depends what you're after. If you're after relatively basic confidential transactions, so where as you say, you're just doing additions confidentially, then well, the reason I actually got into all of this was because the original zero proofs I wrote were exactly to do this. So that's what technically ASIC stands for, anonymous zero knowledge transactions, with efficient communication. Basically, it's you can use the PLONK structure reference string to create very explicit range proofs that are very efficient. To give an example, like you can we've compiled like a join split sigma protocol for confidential transactions down into a proof which literally takes milliseconds to both construct and verify, because you need it's like a handful of elliptic scalar multiplications. So if you're doing very like algebraically simple things like that, there's a good chance that avoiding the SNARK abstraction and just going with sigma protocols will give you better speed. If you want to do more abstract things, like for example, hide the transaction graph by encoding the state of your private transactions inside Merkle trees, and then using nullifier sets to verify spend transactions, then you need to make quite complicated circuits, because then you need to do a lot of evaluations of Merkle paths inside a SNARK circuit, and that's something where something like PLONK, really shines. Yeah.
Okay, cool. Thank you. Another question. Do you think there is a specific hash function or hash function that could work like better with PLONK than others?
Well, I know some that work worse with PLONK. So, for example, things like the Poseidon hash function that recently came out, which was designed to be very efficient in R1CS, straight up isn't very efficient at PLONK because it uses a large number of additions. But things like MIMC should be pretty efficient. I haven't done any hard numbers, but generally, if you're mixing round, roughly has the mixing rounds, I believe, generally the number of additions is quite similar to the number of multiplications you need when you're kind of scaling up your what's it called, your cumulative hash value. So yeah, generally, I suspect it'll be about 2 to 3 times slower than graph. To give some hard examples, actually, some things that I have done is, for example, elliptic curve operations on embedded curves, so things like baby jump jump and jump jump. The efficiency should be roughly, basically, the number of addition gates you need is about the same as the number of multiplication gates. So then it's only 2x slow, which is pretty good for a universal SNARK, I think. But I'll let everyone else be the judge of that.
Mm-hmm. Okay, thanks.
So are there what's currently like the plans for implementation, or should there be more theoretical work first, or?
Yeah, so we basically, Ariel, Rana, and I, we were basically focusing very intently on getting the paper out once we had the idea down. So the next phase is the phase I've been starting is basically actually producing implementations of this stuff. And I know there's been quite a few people being quite interested in this and interested in collaborating. So I'm hoping that we can get a bit of some open source tooling around making PLONK proofs. But yeah, that's still in its infancy. I'll report back in a month. Hopefully, we'll have something a lot more concrete then.
I think I have some questions about the proofs in the paper. I guess it will be based. I posted it in the group, right? Because right now it might not be so easy to discuss in the video chat. It's a bit more technical, but I think maybe later I just ask in the group instead of asking you here.
Yeah.
What do you think?
I mean, why don't you ask it? I mean, if it's something which is going to be, it'll take a while to borrow through, maybe we can take it offline.
Okay.
Yeah, I think what he just mentioned there is he said actually you could say it now if you wanted to, and then if it's too heavy. But we will have to wrap pretty soon.
Okay.
So why don't we ask this question and then we wrap up. So yeah, go ahead, Cheng Wang.
Oh yeah. Oh, cool. So basically in lemma 4.5, I'm curious what would happen if the p polynomial cannot compute the polynomial t, because there's some probabilities the p polynomial could not compute t.
So I'm going to have to bring up the paper and refresh my memory. Just give me, wait, no, that's not my paper. Sorry, give me a second. Just a minute. Four points.
4.5.
What's that? So, sorry, can you refresh my memory? What was your question?
Yeah, can you go to the proof? It's in the next page.
Yes.
So here you see that in the second item it says p polynomial computes the polynomial t equals to the formula. But here there's a probability that p polynomial cannot compute t.
So if I remember correctly, this kind of thought experiment. So we're saying that z does not divide f. And so we're then, wait, no, that's, so let me just try and jog my memory about this. So we're working in the algebraic group model, which is kind of a little bit of a workaround to the fact that Cassie's polynomial covariance scheme isn't actually simulation extractable if you don't make a couple of assumptions about your adversary. And so in the algebraic group model, where the assumption is the implicit assumption is basically that the coefficients of any polynomial an adversary commits to are efficiently extractable. It's a bit of a workaround to do the fact that you don't know the maximum degree of the polynomial an adversary committing to, not theoretically at least. I mean, you do in reality because the structure reference string only goes so high. But it means that basically you can't construct a model where an extractor can always recover the coefficients. So you just assume that this is the case. So if p can't compute the polynomial, then this would mean that so f is supposed to represent some kind of she's supposed to represent some kind of polynomial identity which vanishes the vanishing polynomial. So I'm just trying to jog my memory because this was one of the lemmas that Ariel wrote.
By the way, I think I'm gonna have to bounce now, so we might have to wrap this.
That we can
now you know at least where to look and kind of.
I'll why don't we go on an email thread and I'll CC Ariel and see if we can.
Cool. Thank you.
All right, I want to say thank you again, Zach, for going over this. That was awesome. And I will be putting Adrian, if you can share the link with me, I'll put this up on YouTube, and then we can also share it there. And there are some, I think the question that was repeated in the chat was about implementation, but it sounds like not yet is the answer.
You'll hear about it when it's done.
Okay, cool. All right, so thank you everybody for joining the study club. And feel free also to suggest, like, if you guys want a continuation, or if there was a piece of this where you want to go deeper. Like, we have some really good people here, so. I also really liked this format, and it might be something we consider doing, actually, just like having the author of the paper actually talk through it. Anyway, just an idea. All right, cool. See you guys later.
Awesome.